Bismillahirrahmanirrahim. Welcome to Diode and Application Season 2. Today's topic is Zener limiters, that is new topic, and we want, as the name indicate, we limit the voltage, AC voltage basically we use in the case of the limiters and by using we use the Zener diode and limit the voltage AC input voltage by using the Zener diode. So what is the very simple simple application of the Zener diode? This is a very simple application, so I just prepare one video for this, and I will definitely try to complete this episode by the help of only one episode. For example, this is a Zener diode. Oh, sorry, this is a V input. For example, this is an AC input, and here we have a Zener diode as usual, and we are basically receiving the our output voltage in parallel with the Zener diode. For example, this is our V output, and the graph of the output voltage will be here. For example, this is a limiting resistance diode, and in the first portion, the first positive peak, first half cycle, that is the positive peak in the first half cycle, the positive peak in the positive peak, let's say the polarities are this. The positive peak is on the side and negative is on the lower side, and the positive peak reaches one here. It is the situation looks like this. The positive is at the cathode and the negative is at anode. When the this is the normal region of our Zener diode breakdown, reverse breakdown region and normal operation. So if and a diode is connected in this region, then the what happens, basically voltage is going to increase. When we are going here, voltage is increasing, but when we reaches at our point that is called knee point, and Vz, that is start basically from Vz is almost started from the when we reaches at our current is reaches to Izk till our current is Izm. When the range is between Izk to Izm, our voltage is constant. So when our current reaches to a region that is basically after increasing our voltage, that is Vz. After Vz, it is constant and it is limited or clipped off upper portion. So when again after increasing this further current, there is no change, but when we decrease our further current, our voltage will suddenly decrease like this. So upper portion is clipped off and it's a constant. If for example, in the next half cycle the polarities are changed, and in on I will show this with the different color, a green pointer as usual. So in the next half cycle, this is a positive, sorry, this is a negative and this is a positive. Positive is connected towards the anode, and negative is reaches to the cathode of the diode. This is the normal diode operation. This is the forward bias region and this is the negative region. We discussed this graph already explained here, and the positive portion is as the simple diode, the first season. You remember that season? This is the basically knee of the first season, that is the normal 114,007. This is the same behavior. This is the knee and this is 0.7 volt for the case of the silicon, as usually used is silicon is a normally used, but sometimes if we use germanium, doping is of germanium, then it is 0.3 volt in the case of the germanium. But I explained many times why we use silicon as compared to germanium, because it's more stable and because of the valence shell difference. Okay, here when the diode is in this state that anode is connected with positive and cathode with negative, so it is a forward bias. So when we going toward forward bias, this is after 0.7 further, it's when there is no 0.7 voltage is not reaches to 0.7, then this diode will behave like a reverse bias state. The current is we are receiving at our output, but when we reaches to 0.7 volt, our upper portion is clipped off, because this diode will behave like a normal, a simple wire. There is nothing else. This looks like a simple short circuit. This is a short circuit right now. For example, this is a short circuit. Then all the current is through this. For example, all current will goes to through this side, and the cycle is completed, or a loop is completed. So as you know, current always follows the shortest path. So this is very simple. So we are not getting any output from the V output side, and our output oscillate, our graph on the oscillator, maybe any other screen shows that there is no output voltage. Okay, so upper voltage is clipped off. Above 0.7 volt we are not receiving any voltage, and most of the cases we ignore 0.7 volt and we say that it's okay, we are not getting nothing, we are getting nothing. So we can also say that this is our positive limiter. Okay, this is a positive limiter. We use just a Zener diode. If we change this, I'm again using my marker, if I just change the direction, what happens? Assume, for example, I change this to this, and this becomes basically now a negative limiter. Now see how. For example, in the first case, again positive negative, positive diode reaches, positive reaches here and this negative reaches here. But again when the diode polarity is reversed, the positive is now connected towards anode and negative is connected to the cathode. This is a normal state, and I explained this is a 0.7 volt. After 0.7 volt, this diode will conducting and it behaves like a short circuit, and we will not receive any output on our output scale. So it's clipped off, or we can say that we did not receive any voltage in the reverse in the positive cycle. So this is a negative limiter. Basically, when the polarities are reversed, this is positive and this is negative in the negative half cycle. Then what happens? Positive is connected to the cathode, negative is at anode. It will goes until the situation is Vz, but in the negative side we usually use negative Vz. When the Vz, again the same situation but in the reverse polarity, so negative is clipped off, a negative portion. But if we want to use in practical cases, we use the positive limiter and negative limiter at the same time. So we use the two diodes, for example like this. This is used for positive limiter, and this is another diode that is connected in this pattern for negative limiter, and we will receive the output on this scale. When the first positive cycle reaches, this looks like the polarities is positive. When the positive reaches here, what this diode will basically clip the positive or limit our positive peak. But what happens right now, this diode will behave like an open circuit until 0.7 volt is not reaches. If it basically needs 0.7 volt, the positive is here but negative is not reached here, so this diode will not do anything. It basically increase our output to 0.7 volt. 0.7 volt is increased. After the 0. It behaves like a 0.7 volt resistance or a battery of 0.7 volt in output state. For here in this case, this 0.7 volt is added to the Zener's voltage. You can say that this behaves simply like this graph, but due to this 0.7 voltage is added to the output volt side, because for example this negative is reached to the cathode of this is called D1, this is for example D2. The D2 is in forward bias state. For example, this negative is here and the positive from the upper side reaches to this side. When this anode is connected to positive and cathode is connected to the negative side, this is the forward bias state. In forward bias state, the first 0.7 volt is needed. When 0.7 input is increased from 0.7 volt, then this behaves like a short circuit, and after this D1 will start operation. So 0.7 is basically an external or an additional 0.7 volt output is received due to D1. because D1 will not conduct and it will behave like an open circuit, so the current reaches at output. There is no connection here, so current is reaches at the output at 0.7 volt. Then D1 will start operation, so the Vz of D1 is reaches plus 0.7 volt of output is received. Same in the case if the negative minus Vz, if then this diode will behave in forward bias and this is in reverse bias in the case of the negative polarities, when polarities are changed. So negative Vz minus 0.7 volt. For example, let's talk about let's say discuss an example. For example, this is a diode and we will say that this is a simple diode. For example, this is the input and we are basically getting output here. This is 3.3 volt and this is 5.1 volt regulator or diode, Zener diode. This is R, that is 1 kilo ohm, 10 volt minus 10 volt. What happens at the output side? When the first positive peak starts, the positive reaches here and the negative is reached here. The anode, this is D1 and this is D2. Again the same thing, I am repeating whole process once again. I will summarize the concept here. When the positive reaches here, this diode will be in forward bias state, so 0.7 volt is approximately drop and we will receive the output V output. This is output, what we receive at output. 0.7 volt is reached here, in the output 0.7 is reached. But after that this D1 start conducting, but this, so after D1 can start conducting, but D2 is in reverse bias, so we still receiving output at our output panel. But after that 5.1 volt plus 5.1 plus 0.7 volt, this is total 5.8 volt. After 5.8 volt, D2 will also start basically in D2 will goes in the reverse bias breakdown region, and that is the normal operation, and after that it will start the regulating and we will not receive any further peak of this, and this is called the limitation. That's why we call this is Zener limiter. This process again repeated, and then this will be in forward bias state and it will first drop 0.7 volt and then this will start its operation, that is called that is 3.3 volt plus 0.7 volt, and in this case this is total 4 volt. So after 4 volt this is clipped off to 4 volt and on this side it is clipped off to 5 volt. This is basically negative 4 volt, because I explained here this is minus 3.3 volt minus 0.7, that is minus 4 volt, so minus 4 volt. Okay, this is a very simple application. Next time we will start the varactor diode, that is the important topic, and we will make further and more episodes in the varactor diode. That is an important topic and an explanationable topic, so we will discuss next time. Watch and glow. See you next time.